Everybody, I guess just give another minute for people to join. Okay, everybody, I think 4 minutes after now, I can go ahead and get started. Guess the attendance is a little bit light to start off with. Go ahead, put your name in as an attendee here before we start. So we do have an agenda, some topics. Hopefully you can see what I'm sharing. Can you all hear me?
Yeah, we can hear you.
All right, thanks. So looking through the list of topics, I think one of them we'll get to sort of, maybe an effort to collect new topics. But I do see, Osama, you put something here to go over first on the agenda. So if you're ready, we can go ahead and start with your topic.
Yeah, hello, Jim. Yes, sure. I can start. Should I, if you could stop sharing the screen? Okay, just a moment. I hope you see the screen now.
Yeah, I see it.
Okay, perfect. Yeah. Yeah, I Dan asked for like the progress of what the SIG has been doing for some time, like last year, I think. So I tried to kind of capture this as a few slides, also including some discussion of what we are up to in the SIG, covering kind of all the 3 projects. So that's been a joint work with all of these people and even more, and probably forgetting someone. Yeah, so I want to start basically with where we were in the SIG when we started with architecturally defined attestation, going over to attested TLS, and then some open problems that I would like to see addressed by the SIG or being discussed at least at the SIG. Right. So this basically this is the top level view that we have created, kind of to see how this TLS based architecture differs from the architecturally defined attestation on the right, with one having the CA or the certification authority as the trust anchor, and on the right, the hardware manufacturer as the trust anchor. And the kind of discussions that we had was mostly on this side, because this side is probably much more clear, formalized, and has security guarantees. The CA providing the public key to the client and server requesting a CSR and being issued a certificate based on its private key, with which then it runs TLS protocol. And on the right are a few ambiguities. So this is basically a typical scenario which I have, and I would like to see if this is not capturing something which is there. The hardware manufacturer providing the attestation key inside the attester at the manufacturing time, typically, and providing the or making the public key available for the verifying relying parties. Basically, it's a very simplistic view of two parties, meaning that the verifier and the relying party is combined together here as a verifying relying party, just to make it analogous to TLS, to see how to combine things together and to analyze them more formally. Then they can be separated, and we have started some work in the background check model. And there are synchronization problems there. So basically, we start very simplistically with this. And instead of specifically having TLS, this is the interaction model, which could be challenge response. And I think is, to my knowledge, is always challenge response. And I would like to hear if there is anything other than the challenge response model that is used for attestation, meaning without combining it with the TLS. So this is only attestation by itself. There is no TLS yet. And as always, feel free to speak up if you have any thoughts or comments or questions. On the left, we have the certificate signed by the private key of the CA for the identity of the server and the public key of the server. And analogous to that, we have evidence which is signed by the attestation key with containing the measurements and the public key corresponding to this private key for the tester. And Jacques, go ahead.
Yeah. Hey, Thomas. Hey, Osama. Jag from Oracle. So I wanted to quickly share my thought and confirm. So we're talking about TLS versus architecturally defined attestation. So
Right.
which one is more typical is kind of what I was thinking when you were opening on this topic. And to me, it looked as if the TLS-based approach would be more typical because most TEs in the cloud are VMs or containers, and they don't have access to a hardware root of trust. So they have to bootstrap trust from a CA using a CSR. Is that a valid statement? Or if there is a way for a TE to share the hardware root of trust in a virtualized environment in the cloud.
So if I understand your question correctly, you are saying which one is more typical, this on the right or on the left? Is this a good summary of your question?
Yeah.
Okay, so I would say for now, this is actually not describing or kind of comparing anything concretely. This is only saying this is RFC 8446. This is RFC 9334 with two rules combined together. And actually, the question you asked is very interesting because this is one of the open questions that we also discussed and also on my last slide, that is there any so since you asked, then I will pose a counter question to the SIG basically, or to you as well, which is we were trying to figure out if there is any protocol which is actually using this without any secure channel, like TLS, like noise, without any secure channel. Is there a real use case where we use only this protocol? And I think Thomas was the one who pointed out that key release or KPS could be thought of as one possible use case of this one. I still believe that runs on top of TLS. So this is a bit fuzzy thing, which we are trying to clarify. And I would like to know if people have any thoughts on any use case on pure architecture. Greg, please.
Yeah, Azure has a secure key release protocol that, there's TLS involved, but it's not used. It's not attested TLS. So the attestation is essentially at the application layer, and it's a secure key release protocol. So essentially the diagram on the right is implemented. And TLS is involved for the communicating parties, but it's immaterial for the diagram on the right because it's not attested TLS.
Okay, so you are saying, but just to be sure, so you said TLS is involved, but won't you say it's
Well-
a kind of post handshake that you establish TLS and you do attestation on top of that, isn't it?
The protocol is basically the trust in the results is based on exchanging or sharing signed information, being it signed attestation evidence or signed tokens from a verification service. So I have to go and actually look at in details of the flow there to say exactly what's the value add from TLS. So I'll just say that the protocol, the high level kind of logical protocol doesn't take a dependency, as far as I know off the bat, on TLS. It is basically an exchange that, basically it's just like this diagram here, it's moving around signed attestation evidence, signed attestation results, and relying parties make decisions based on, that. So.
Okay, very interesting. If you can post the link to that, we will also like to explore that.
Yeah, I'll dig up some links. I suspect it's not going to be. It's documented essentially as a product and how you integrate. Maybe product's the wrong term, but as a capability of a particular service in Azure and how to integrate that with different in different circumstances. So it's there. I'll share what links I can find and that touch upon it or that describe it.
Sure, that would be I think the most interesting takeaway from this is the question how much dependent that is on TLS, or what is the dependency. And I think it was Thomas again who pointed out that should we define attested TLS as the question here is what's the boundary between this and attested TLS? So which way we define the two terms very precisely so that there is no gray area in between. And one view probably coming from Thomas was that if there is channel binding between the two, we define it as attested TLS. If it runs on top of TLS, but there is no channel binding, and that's what I think you were calling as dependency on TLS. So I think that would be the most interesting perspective to look into in this key release that you were mentioning, that how much dependency or channel binding exists. That's the most interesting perspective for me to kind of define formally, hey, this is what we call as architecturally defined attestation, and this is what we call as attested TLS. So that would be very helpful if you could share some links in that direction.
Yeah, I'll share some links. I'll take it up in a bit.
Thanks a lot. Thanks. Thomas. Oh, sorry, Greg, go ahead.
No, go on.
So no, just piggybacking on what Greg was saying. So the key release, when you do key release, at least the things I have not looked at the Azure protocol, but KPS, for example, in Coco works that you need to have. So basically, there's a key that is bootstrapped, right? So and you release the key over the secure channel that is protected by the key that is attested as part of the workload. So the back channel is in a way a secure channel, right? So, but it happens at a different layer than the transport. So I don't know whether you can call it attested TLS because there's no TLS involved there. But there's a secure channel that that is established on the backwards direction, right? So after you send over the attestation with the key in it.
Is there any channel binding there? So is this process, which is this challenge response model there, is it dependent? Is there any dependency of that on the TLS protocol?
No, I don't think so.
Yeah,
Okay.
for SKR in Azure, I think speaking the way you're thinking of things, no.
All right.
But it's a secure channel, right? So depending on how where you put the sort of when you draw the line is the important thing. So you drawing the line TLS as a a specific secure channel establishment protocol, or are you thinking about secure channels in general? Because that's a slightly different question with different answers.
For me, I am fine with having any secure channel, and I'm trying to distinguish, or I'm trying to see how does this architecturally defined attestation distinguishes from attested X, where X is, let's say, TLS or any other secure channel within the context of confidential computing. Let's say, if we remain within that context, the ones I am aware of is TLS, and Google recently announced this noise. So let's say X meaning TLS or noise. So that's what I would like to distinguish, that when do I say that is attested TLS? And I think the most ambiguous thing is about post handshake, that if it runs on top of TLS or noise, and then we do this interaction model on top of that, would we call it simply architecturally defined attestation or attested TLS or attested noise? That's probably something
So I
that
think
I'm looking for.
one discriminant is the binding, this channel binding.
Yeah.
Actually, it happens. That's a clear signal, but that's my point of view.
Right. Okay, cool. Any other ideas from anyone else? Okay, if not, then I will proceed. So the right side of the picture, now I zoom into that, and there is an architecture perspective to that. There is also the protocol perspective, and which I have in the next slide. This architecture perspective is much like RFC 9334, just combining verifier and relying party, making things simpler to solve or to make it formally analyzable, because then we could have two parties for TLS, two parties for attestation, and then we could do, and as I said, if separating the role leads to issues, and that's the main reason. So we have, according to RFC 9683, I believe there's three divisions, which is generation of evidence, conveyance of evidence, and appraisal of evidence. Conveyance here for architecturally defined attestation, meaning this is the challenge response model. And if someone is aware of any other model which is used here, please let us know, because this is what we have formalized using this attestation challenge or nonce coming from this, and then an evidence being generated. Right. As I said, there is a, yep.
Sorry to interject here.
Thomas. Yes. Yeah.
Just clarifying, the use case is confidential computing, right?
Right. Yeah.
Different things like trusted path routing or anything like that.
No, so the context within all of this is only confidential computing.
Okay. Otherwise, I have other models, but they don't apply.
Okay. Mhm. Yeah, so we are just formalizing it only within the CCC context. Right. And for others also, if you have any thoughts, feel free to let us know later as well. So I will move on. What's most interesting for us formally is the protocol perspective. I mean, this architecture is interesting, that's nice, but we just assume that these things are happening nicely, meaning perfectly from a formal perspective, that an attester is already provisioned with an identity. All of these things are available to the verifying relying party, much like the figure that I had. So everything on top is already done. And what we only analyze is this interaction protocol or this TLS protocol and seeing how they combine together. In that sense, it's very interesting for us to have the protocol perspective, what happens between the two parties. And this is the keys which are pre-provisioned, and sending a nonce, generating evidence, conveying it over, and appraising it with an integrated attester, meaning both environments, target and attesting environments, are integrated. And if they are separate, it will send over a nonce. Target environment can, in addition to nonce, send some random user data. And on basis of that, then it will proceed accordingly. So what we can do from both of these is combine them together. And that's basically because of the fact that TLS and architecturally defined attestation are giving us very different properties, which is, this is saying what is the state of the attester, and TLS is establishing basically the secure channel. So they are both orthogonal to each other. And in most use cases, one would like to have both. And that's where we have this figure, which is kind of defining, or more precisely saying that this generation of evidence contains 3 steps, that it generates claims, then it basically collects claims and then signs claims. And the signing is the part which is most important cryptographically. All the claims are then protected. And if we do it before TLS handshake starts, it's pre, in between is intra, afterwards is post. Just as a recap, we have discussed this diagram many, many times. And this is really important, but I always put it in there because I get the question that, okay, so is it pre, intra, or post? And people can't answer that, whether it's pre, intra, or post. And it's really the top layer of the whole thing. If someone can't really define their design as one of those 3, it's really a suspicious design to me, that they don't even know about TLS and attestation, and then the design is very suspicious to me. So to help people, what we have done is basically categorize the solutions which are known to us already, and pre, intra, and post. And specifically, I will highlight the projects that we have in the SIG, Intel's RATLS or interoperable RATLS. We have analyzed that one formally. On this side for intra, the internet draft TLS attest, we have analyzed that. And we have a project in post handshake for KBS, and it's a question mark whether we call it post handshake or what exactly we call it, or do we call it architecturally defined attestation. But that thing exists. And the new thing is that we have a new draft based on RFC 9261, which I will post in the Slack to, and feel free to give us any feedback on that. So we are starting to look into this because of the problem that I highlighted in one of the meetings. I have the slides again for further discussion. But these are the main design options that we are aware of and which make sense to us to have a secure and reliable and performant solution. Right, so we talked about channel bindings. This is the picture which is showing exactly that. And the idea here is that pre, intra, and post, it's a specific variant of pre, namely for this Intel's RATLS or interoperable RATLS, that, and the boxes are actually showing time going to the down. And this point in time is when the nonce is sent, and the endpoint of the box is basically, or more precisely, I can go back to show this. This is the nonce and this is the appraisal. So this whole thing is put inside as one box. And for TLS, it's the standard. So the client hello and up to client finished, that's what it's representing. And in pre, we have the nonce sent over, attestation evidence generated and sent over as part of the TLS, but the appraisal happens within the TLS before the client hello is, client finished, sorry, is sent over. So that's why it's showing like this. And more specifically, the binding is, so basically the diagram is showing both temporal as well as bindings. The binding is between the this attestation protocol via this evidence sent over to the TLS handshake. In intra, and more specifically in the internet draft or the CCC SIG project that we have, is it defines a new exporter containing both contributions from client hello and server hello. The early exporter contains only the client hello. That's why there is a new exporter defined here, which contains contribution from both client hello and server hello exported to the remote attestation protocol. And then the evidence generated sent back to the TLS handshake. And then it's finishes here. On the post handshake side, basically TLS protocol or TLS handshake protocol more specifically finishes and sends over exporter over to remote attestation. Everything from the nonce is sent up to the appraisal is sent over afterwards on that specific secure channel. Right, so I will then go to the open problems that we have quickly discussed in one of the meetings, and I would like to see if there are any opinions in the meantime. So this is the problem with the internet draft that we discussed, which is specifically we improved the graphic to show it more clearly. This is the TLS client. This is then one of those is the servers, and from remote attestation perspective, this is the verifying relying party, and these are the attesters. And it has in its trust store both the keys, let's say both machines trusted, the public parts of these attestation keys in its trust store. And what happens is this is the VM that it provided with some specific measurements M1 and correspondingly an ephemerally generated key priv EK1. And underneath there is a lot of stuff, coding agent, PC, if that's Intel, and then firmware, hardware. But just to abstract all of that, it's just showing the coding agent as a general thing for coding enclave for Intel SGX or TDX, and for others like any agent which is or entity which is actually generating the evidence. And the thing that happens is that instead of connecting to this, the CSP in control of everything according to the CCC threat model, saying that the adversary is completely out of TCB, it can divert it to any machine that it has. And if one of those machines has been compromised, more specifically meaning that the attestation key is available to the CSP, it can generate an evidence of desired measurements by the verifying relying party, meaning this actual measurements, which it anyway knows, or it can compute from this when it's sent over to it. And then instead of associating with this key, it will associate with the key of its own VM, which is not the same as this. Of course, it is different from that in order to gain this key, but it can still make it believe that it has this this measurement because the signing key is now available to the CSP. And that's how it can convey over the evidence following the protocol. The verifying client party or the client will accept that evidence because it will see that it has the right measurements, it has no identity. And that's the main problem, that it should have two roots of trust, which is what we propose. Fritz.
You were faster than I could find my mute button. I still don't. So we had this, I think, already in the past, this slide, right? So
Yeah.
I'm still not sure I get it, or I get the attack that you're outlining here. So in my understanding, you may want to connect to a genuine machine, right? Sure.
Yeah.
But so what distinguishes the compromised machines from the genuine machine? If the CSP can corrupt the compromised machine, why can the CSP not equally corrupt the genuine machine? Because it will only attest itself as being the same if it is the same, right?
So it could be a different machine. For instance, it could be a different family of machine. It depends on in my understanding, it depends on the compromise.
But it would be in your, it's in your trust scope, right? So it would be a machine, or it would be a setup that the client trusts.
That the client
Because
trusts. That's
it
correct.
has to
So
test
it has not necessarily attested, because it depends on the design of the verifier, basically. And typically, the number of machines that you trust is a very big test, like a big database. Like how can you actually trust each and every machine which is there in the CSP? Like
you don't, right?
about,
What you do is you trust a class or a set of machines together with a given enclave version or given program version or hash that runs on these machines. Of course, if you have a blind verifier that just accepts any machine that runs the code, yes, I believe that, but that's not a smart verifier, right? Ideally, you reduce the number of machines that you want to run this on, or the configuration of machines you want to accept to the set of configurations that you do trust. And then if you have a compromised machine, what distinguishes this machine from the machines that are genuine in this slide? Because then the CSP can equally, it seems like a fair game to me. I don't fully understand whether this is an actual attack or just the nature of the problem of attestation, where if you have an attack on a machine, then well, that's an attack on a machine. so of course you get scooped.
So maybe I try to clarify it further. So one point is that, let's say there are 7-digit machines in the CSP, right? And considering it within the CCC threat model, I don't see any reason why this one machine, let's say, compromised by any way, whether that's by whatever way it has compromised, why would it tell the verifier that it has compromised that specific machine, right? So that's basically the point. And it could be one, it could be more than that. If it has multiple within the same family and it has compromised via some, let's say, hardware attack that applies to all machines in that family of, let's say, machines. For example, some specific Ice Lake or Sky Lake or whatever that specific one is. So it can, of course, then compromise other machines as well. So I don't find that distinction between like this and this is very important. So what we are saying is a very simple game, which is that if an adversary is even able to break a single machine, and that's it. So that basically leads to problems for all other customers. So then it can start to divert to that specific machine. And why would the adversary actually tell you that, hey, this is compromised? Because I think what we need to do is to think of the CSP as a real adversary, and the real adversaries are actually hostile, and they would not tell you that, hey, we have compromised this. If
well,
it's later
that's
on,
what you have the honest but curious model for, right? It's not that you see the CSP as malicious, but you see the CSP as an honest but curious agent, where you expect the agent to behave honestly for economic gains, but curious and interested in lowering efforts and interested in kind of peeking behind the curtains, right? In normal words, that's saying that yes, the CSP is very interested in compromising either to, well, just not use a TE at all, right? If it's because it could be cheaper, or to look at what's going on. But it's also not usually fully malicious in the sense that it's, I don't know, breaks availability or things like that, because, well, that would be detected, right? So that's this honest but curious model.
I have one question there. So when you say that that would be detected, how it would be detected?
Well, if you shut off the machine, that's an attack, but it's detected by the client, right?
If you shut down the machine,
if you shut down the server, it's like an attack in quotation marks, but it's easily detectable by the client that the machine is not on. Right?
I didn't follow that. So how is that an attack? I mean, that's basically a denial of service, right? So it's no longer serving that client. It's basically saying that this machine is. What I'm struggling to see is that denial of service is out of scope of confidential computing. You can always do that, but this is not denial of service. This is different.
Yes, exactly. But you need to clearly define your threat and attacker model. And cryptographic attacker models usually are like, or historically have been like fully malicious attacker, etc., etc. And that's when this honest but curious model came out and served as like a nice middle ground. So it actually predates TEs, right? So this is predating TEs now. This is actually where the availabilities out of scope came from, because it's like the attacker indeed is not interested in availability; it's interested more in confidentiality or integrity. So I was more, sorry, it was maybe like an academic X-course. I was just trying to pinpoint the like exact attacker model we talk about, because well, we can fall back to like terms that are out there. We don't have to kind of be vague, right? So specifically, the honest but curious model we can use here. But what I was trying to get at is, indeed, the CSP is not interested in proclaiming that they broke VM2, right? But I don't see, but if the client trusts the class of VM1 and trusts the class of VM2, and the CSP can break VM2, then this is within the threat model. Like it is assumed that the CSP cannot break compromise the class that we trust. And if it can, then we shouldn't trust this class. So I totally see what you're explaining, but it's not an attack. It's within the threat model that this is, well, possible. We assume the CSP can't do this. And if you can, yes, it's a problem, but it's not an attack.
Okay, so what I would say is that how would you actually say that it cannot detect? I mean, it's then an interpretation of a different threat model, right? So you are saying that if this is compromised, then it doesn't trust it anymore. But then the question is, how does it know that it's compromised?
You don't, which is, yeah, maybe Keith, go ahead. Another voice is always good here.
No, I think I'm agreeing with you, Fritz, here. Last time we discussed this too, I had a little bit of a hard time understanding what the new kind of attack that's being called out here is, because this is no different than VM1 being compromised and VM2 being, genuine, and you're just targeting the targeted machine, or the compromised machine. And like, if the CSP has the ability to attack a specific class of machines, it shouldn't be trusted. Like you should only be targeting VMs that are running on a class of machines that, as far as you're aware, cannot be compromised by the CSP. Like that.
I think the main point, Keith, here is that it should not be trusted is a different thing that it is trusted. So actually, so what you are assuming is an ideal case that, okay, so if this was compromised, it would somehow magically know that it has been compromised, and it would just stop trusting it, I don't think that's a realistic scenario.
No, I don't think so either. And that's not what I'm saying at all.
Right.
So you have to rely on like the best industry knowledge about what types of machines can be compromised or not. And that's what, disclosures are about. That's what like patch windows are. Like if you have an attestation from a machine that has a disclosed vulnerability in that and it has not been updated, you can make the decision not to trust that class of machine.
And class can also mean things like security version number, right?
That's what I meant there. Yeah, like the patch revisions. Like if
exactly.
if this attestation that you've received is of a type that can be forged, then you shouldn't trust it.
Yeah, I would say just say your trust policy should include the TCB level of the platform. So if it's a known vulnerability and it's been patched, then your hardware root of trust should be able to prove that a patch has been applied. If you've broken the hardware root of trust, well, I think it's just broken.
Right.
And in the end, it all boils down to risks, right? Clients saying, I trust VM1 with its security version number, whatever 5, and the underlying hardware with this firmware. I do not trust anymore the firmware 1 week old because I don't know, my policy says anything that's older than a week I don't trust, right? So that's all risks that you account for when coming up with like a policy. But in the end, it boils down to if you make mistakes in these assumptions, and the CSP can or the attacker can compromise any of these machines or any of these classes in your policy, well, then you're out of luck. Then you did a wrong evaluation of your risks and what you can trust. And anyone organizing your infrastructure like the CSP is can easily redirect you to a machine that they can any of these machines in that class, right? So I think this is within total normal risk and policy assessments that you have to do regularly. But yeah, I'll yield now.
Yeah. And I think a lot of this comes down to with a cloud service provider, there is some amount of fungibility that's assumed amongst machines, and you really have to treat things as equivalence classes, right? Like there is a certain property of machines that make them equivalent for your purpose, whether that's the generation of hardware, the patch level, the SVN, whatever it happens to be. These are equivalent, and if you believe that the CSP has the ability to make that not secure, then you have to believe that the equivalence class as a whole have the ability to make not secure. I think the difference between diverting to a different machine of the same equivalence class, I don't think the diversion makes any difference, because if they have the ability to compromise a type of machine in that equivalence class, they have the ability to compromise VM1.
Yeah, but think of
VM2 doesn't change anything.
But think of this as one equivalence class and this one as another equivalence class, and there could be just one of those that could. So the point here is not really within that equivalence class, but across different equivalence classes. That's the point.
But that's visible in the attestation.
Yeah,
that you've been redirected to a different equivalence class. They are not.
What makes them unequivalent? And if is it measurable? If you can measure that they're different, then you can distinguish between the two. Right. So what is it that if they are identical, then it doesn't really matter? They're both vulnerable. But if they're different, one is genuine, one is compromised, how do you make that distinction? Typically, that's going to be through attestation.
Yeah, if there is something that makes them different, that makes one compromisable and one not, and it's not captured in attestation, then I think the attestation is broken. There needs to be that distinguishing factor needs to be part of the attestation.
But that's also a little bit besides the point, right? Because the client in the beginning decided to trust both classes. And that's the choice that the client made. Like if the client decided in the beginning to only trust one class, that's the most constrained, at least for this attack vector, the best way forward, because then you're either fully compromised or not fully compromised. But if the client decided to trust multiple classes for convenience, for availability, for other reasons, then like you get the unison, like the union of all attack vectors, because any compromise of any of the classes in your set breaks your guarantees, right? But that's how this works.
Right. Like that's a decision you make. Like if you lump together different distinguishable factors, but don't distinguish between them and make them one equivalence class, then anything inside that boundary of your equivalence class, like you have decided to trust it.
I think perhaps another way to phrase it is the verifier, the relying party over here, it has embodied in its verification logic what it chose to trust. And that is that's the thing that needs, needs to reflect it. They get full control over what they choose to trust. They may choose to trust 50 equivalence classes, 1, 1,000,000, that's their choice. And that should be based on, their risk assessments and so on. But and if they get a response from something that ends up being compromised, and then they end up trusting it because their database of what to trust over there says to trust it, that's not, as people are pointing out, that's not because things were diverted. That's because something about how that trust was set up is broken. Perhaps the fact that a particular SVN of some firmware can be compromised isn't yet recorded and available for the world to understand and update their verification policy. But I think that the crux of the matter is what they choose to trust. And if basically what you choose to trust, if your correctly configured verification logic ends up trusting something that's not trustable, that means it's either an exploit that's not been, published yet and folks are aware of, or something else that's fundamentally busted in the system. That's what I think we're saying here.
Right. I get your point. So the only thing I want to emphasize again is that typically this trust store is who is kind of giving you, I mean, this is just a very simplistic diagram. So in reality, this is an IP address, right? So this is not really a public key. So that would be more of an IP address, and that IP address is issued by the CSP itself. So you are talking to an IP address which is assigned by your adversary itself. So how would you?
But the trust decisions aren't made on, that's not part of the attestation evidence, right? The attesting environment provides all sorts of measurements, signed up through a root key from the hardware vendor of, what's been measured. And it's things like, what are the SVNs for the firmware that are running on these, in the CPU, et cetera, et cetera.
But that is after. But that is after attestation, right? So we are talking about this trust store is this IP address is given to you by the CSP before doing that attestation, right? So it's not.
But the thing that's busted here is the remote attestation part, right? It's you've made a judge that the verification logic verifying the attestation evidence for the orange colored rectangles has chosen to trust those orange rectangles based on attestation evidence. And that's where the issue hit this whole system, right? And it's because so
I would say it's not based on attestation. I mean, think of a realistic scenario. I mean, I don't see it realistic that I, as a client, would go and let's say check each and every machine of the CSP
no, but you're not
which
checking
one I trust. Yeah.
I mean, in like number 5 there, it says appraise and accept evidence, right?
Yeah.
So that is looking, if it's looking at evidence, it's looking at signed quotes or reports, whatever you want to call it, from essentially a hardware vendor. right? And
Right.
so it's determining whether to trust it or not based on endorsements, CORIM endorsements, or you know, hard-coded root CA keys, whatever. But there's some policy there that says whether to accept it. That's the part that's busted, and that's not busted, but that's the part that leads to accepting the orange rectangles, which are compromised. So the qualities that make it compromised are not recorded in that, you know, the policy for that appraisal step number 5. Right? So that's the fundamental issue. How did that happen?
So
How
I
the
would
heck did
ask
that
you,
happen?
I would ask you the other way around. How the heck is this client going to know that this has been compromised? How is it going to
No,
remove
no,
this
no.
key to say that this has been compromised or this key has been compromised? How is
But I
that
think
going
this
to
problem
happen?
exists totally independent. This could be a non-TLS scenario. Someone's just trying to do, let's just say, for example, Azure SKR, right? Nothing to do with doing a TLS. It's just like, here's some attestation evidence from that orange rectangle. Do I trust it? Am I going to release a key to it? That's a total remote attestation problem, right?
Right. So that's basically, I have it in this slide, which is this kind of this KBS thing. And I agree with you, that happens also independent of TLS. But the way or the reason why I'm talking specifically about TLS is an inherent problem in the protocol that we are verifying, is namely that it's not providing you the identity of that specific machine. If I would have that identity of this specific machine, I would have to, I as an attacker or CSP would really have to break out this machine and not do one out of these 7-digit machines in the CSP. Any one of those would not be.
Yeah, I'm clearly not totally understanding you, and kind of per what Keith and I think others were saying, in a CSP environment, you really, the customers, you know, really have to understand that the machines behind the covers are fungible. They're moving around, they're coming up, they're going down. It's like, so any sort of design that is basically taking a dependency on a particular machine is going to be problematic for all sorts of reasons. So they really need to be, as you know, to work in a cloud-based environments where there is no guarantee of particular machines. And the structure of the policy and the trust has to really be on these equivalence classes. Like this, I'm going to treat these sets of machines equivalently. I'm going to describe some, you know, understand some description of a set of machines that I'll then judge as trusted or whatever. But you know, trying to pin things to a particular machine. This was the machine I had yesterday, and you know, I established trust in it, and now today I have a different machine, or I insist on the same machine. That's gonna, you know, that's not that's not a circumstance that cloud customers can't really structure things that way, because they can't rely on, you know, particular machines remaining the, you know, consistent over time. Yeah. So
Yeah, sure. But they have to, these clients then have to take out the risk or understand the risk that basically if the CSP happens to break any one of those machines, it's game over for them. And
I
they
think
wouldn't.
so I may not, you may have a fantastic points to make. I don't get it beyond the point of kind of like, hey, anytime anybody's able to break a TEE environment without the world knowing that there is a break in some component, some, you know, the break is somewhere. You've compromised some firmware, some system software somewhere, without the world being able to know about it. It's like a 0 day. It's like they have some window of time where they can abuse this thing till the world catches up and says, that version of the firmware is compromisable through attack X, and then that gets out a new endorsement saying no longer trust, you know, firmware with, you know, SVN X, and everybody updates their policy and, you know, number 5 over here, and then that issue is kind of sealed. But beyond that, I don't understand the you know, what you're trying to share here myself. Not saying it doesn't exist. I'm just still not getting it.
We have a question too.
Yeah, I think for sake of time, we're almost out of time, and Jag's had his hand up for a while. Maybe we can address that hand and then wrap up.
Sure.
Yeah, I wanted to quickly ask a question, but since we're out of time, if you want to finish it, maybe I'll post my question or comment on the chat.
I think it's fine. So you can ask. So maybe I will. We have already discussed this thing. So I had some questions for discussion, which I will maybe follow via mailing list or something. So you can ask.
Okay, so in this context, the AK, I'm assuming it's the attestation key. It's typically associated with.
Right.
Thank you. Okay, so in this case, you're saying that a compromised AK, private key of the AK, which means that the TPM is broken, right? Because AK is something, in my understanding, that the TPM stores secretly, never exposes, but it only uses the proof of possession of AK to establish identity during a handshake with a certificate authority. So if AK is compromised in the context of TPM, it means that the TPM itself is compromised. So
maybe just to clarify it very quickly. So this is not mentioning about TPMs. So here we are talking about TEs, meaning that this would be one of the Intel SGX or TDX, and this, let's say for TDX, this would be the quoting enclave and not a TPM.
Okay.
So the context here is not TPM or trusted computing. I mean, it's more, or it's actually only confidential computing. TPM could be used in association with that or VTPM, but it's that's kind of orthogonal to all of this, meaning that this is a quoting enclave which has this key and it uses that key for signatures.
Okay.
Go ahead.
Okay, so just like 15-second comment.
Yeah, sure.
I really appreciate what you're doing with ID. That's something that I was also wondering about and understood that TPM addresses this problem. But if the agent is broken, it feels as if to me that the whole thing goes down, because that's where we get root of trust.
Right.
Let's have just a quick question about the timing. Maybe this is a temporal issue. Is the appraisal and evidence evaluated when you put the pub AK into the trust store and you don't audit it afterwards? Meaning that when you did the remote attestation of pub AK2, everything was good, but some vulnerability was found. There has been some patch published, some type of security announcement and or advisory, and then you now have this compromised key that needs to be re-audited. Like, is the question about, is it a timing question? How do I get it out of my trust store if it was once considered trusted, but now has become untrusted and it's measurable? Do you have to reattest? Is it the lifetime of that pub AK that you have to go and ask for, remote attestation or some way to reattest after trust has been established?
Right. So basically, to summarize, basically your question is that once you have done one attestation and AK was trustworthy at that point in time, how has it become untrustworthy? Is it good phrasing of your question?
Yeah, right. There's some vulnerability that was detected or exploited after you establish trust. So really the issue is that it's a temporal question that I can't, right? The lifetime of that attestation key is limited by the frequency of attacks, exploitable attacks.
Right, but at the same time, the certificates are also valid for a period of like 7 years or something like that. Like the older certificates are still valid for, and I think that goes maybe in the same direction as Greg's question, that I wouldn't, as a client, go and check each and every machine of the CSP. So it's still questionable to me when you say that it was attested at one point in time, how it has become untrustworthy. So that's an important and interesting perspective. So we will actually look deeper into it, and in some point in time in the future, we will share some insights on that.
Okay, we've reached the top of the hour too, so probably wrap
Yeah.
up. But I did put in here in the notes, we'll continue these attack discussions. Next meeting, we can continue them offline as well.
Sure. Thanks a lot.
Thanks, everybody.
Thank you. Bye.
Thanks.
Thanks, all. Have a good day.